So hello everyone, good morning. Very nice to see you here at this session, the last session I think out of 43 panels this week, so you're very brave to join here now on a very forthcoming and future topic, which is quantum machine learning. We'll go a bit more in the details. Actually, I'm very glad that there is a very young member in the audience, because actually this is all about him, because everything will happen more in his career than maybe ours. Anyhow, I'm Karolos Potamianos, so I'm a particle physicist. I'm a professor at the University of Warwick in the UK, and I'm working at CERN. And I'm here today because I've been following AI for a long time and machine learning tools since a bit longer. And being a physicist, we study very much the quantum world. And it's very exciting to actually be able to have an outlook as to the fact that we can actually combine the two and get something possibly useful out of this. So we'll explore this together. Obviously, we're familiar that maybe not everyone is familiar with quantum computing, so we'll talk a bit about that. But then also look at what and how can we combine quantum computing with machine learning. So here I have with me Heike Riel from IBM Research. So she's the lead of IBM Research on quantum in Europe and Africa. And she joins me today to basically discuss a bit about all what's going on in the quantum world in terms of computing and more particularly maybe on quantum machine learning. So I don't know if you're aware, but a couple of days ago came a roadmap on the quantum economy. It was a report published by the WEF, a blueprint, I think on Tuesday. And it really outlines how the quantum economy will be, shaping the future. It's very far away, but I think we should start at least talking about it today and seeing what it is. So Heike, I don't know if you want to maybe tell us a bit about you before we start. I already spoke enough, so.
Sure, I can give you a bit of more background. I'm by training a physicist, and I have been starting my career like about 25 years ago with my PhD, working on things which you wear on your hand, because I was developing and researching these organic light-emitting devices, which we all use for displays today. And then I moved on to do transistor work for the next generation of classical computing, right? And I was always like working two generations ahead or even more. So I studied in 2004 on nanowires, which is actually now coming into the products. So you see also hardware cycles take quite a long time in order to bring that from a research into then development and then into a product. That may easily take like 10, 15 years. And and then in 2015, I started to work actually in the US on quantum computing. And now I'm back in Zurich, leading in Rutherford the IBM research part on the quantum computing and also AI hardware. And I think computing in general is a very, very interesting topic. It's at this time, let's say, much more dynamic and interesting than let's perhaps go 10 years back, because there you had miniaturization over many years and you just had to make things smaller and you got more performance, right? But this is done. And therefore we need, as engineers and physicists, become more creative in order to squeeze out more performance. Because without compute performance, you won't do AI. And I think at WEF there was a lot of discussion about AI, and I'm sure you all have been participating in some of them. So AI and anything you want to do has to do with compute performance. Whether it's research science, I mean, that's your topic, right? I'm sure you will talk about that later also. And so compute performance is a core of the evolvement of the technology. AI can only become better if compute power becomes faster, more, and at less energy consumption. And this is what we worry about on a daily basis. And things have become more complex. That's why we also need different types of computing in order to increase the performance. 10 years back, we had one processor. You could do everything with this single processor. Today, if you want to do AI, you do an AI accelerator. If you want to solve other problems, we talk about that later, then you use a quantum computer. So there are many different things and it's becoming, from a research point, much more exciting, but also more complex.
Thank you very much, Heike. So it's indeed exciting to hear about all these prospects. And I have to say I appreciate very much the fact that also in industry people do long-term research, and it's not just left to academia to say that, okay, academia typically does the research, and if there is a nice spin-off opportunity, everybody jumps on it. But there are really companies out there that actually do this on the long run. So since we want to delve a bit more into the topic, maybe let's start a bit saying, okay, what's a quantum computer and what makes it so special? Like, how is it different from the regular computers that we are now using on our daily lives?
So I don't have a picture with me today, but if you look at the picture, then you already see it's completely different. And so when you look at classical computer, then you all know we are using transistors. If you look at your processor, it's made out of transistors. And there are like 100 billions of those transistors today in a processor. And you use bits, which is a 1 and a 0. And at like each point in the information processing, you know exactly which bit is which, whether it's 0 or it's a 1. And so it's really based on a classical physics. And if you go to quantum computing, then this is a new type of computing which is based on quantum physics. And quantum physics is probability. So you have you use quantum bits instead of bits. And these quantum bits, they can store much more information, because if you look at it mathematically, it's a superposition of a state, right? You have a 0 and a 1, but you have all the, if you look at a vector, right? It's you can let's represent your 1 by an arrow up and your 0 by an arrow down, and then you have a superposition, which means that you actually have like a sphere, which can be, which is the content of information you can use in your calculation. So you can store much more information in a quantum bit than you can do in a normal bit. And this provides you then a possibility, together with some other strange phenomena like entanglement and interference, which you can utilize to then make much more complex calculations that you would be able to do with a classical computer. So to give you an example, when you want to calculate, and that's very simple, perhaps a bit just to illustrate, right? If you have a molecule, let's say it has 100 electrons. So if you want to calculate the properties of this molecule exactly, then you have to write down an equation which shows all the interactions of these electrons with each other. And this equation is so big that you will not be able to build a computer which contains the information in this equation. And that's very hard to imagine. That's really very hard to imagine. Why is it the case? Because of the exponentiality of the problem. Right? So even if you have, another example, if you have like 12 people which you invite to your birthday, and you want to place them at tables, right? Then you have a probability of almost 3 million to kind of place them at the tables, right? And so this is exponential behavior, which we're typically not used to, but in math and physics, it's present. And a quantum computer can make use of an exponential behavior, whereas a classical computer cannot. And so the molecule of these 100 electrons could, in principle, and so be calculated then with about 200 qubits, if they are ideal, right? So you see, I only need 200 qubits, but I cannot build a classical processor at all, also in the future, even if it build it bigger, which can solve that problem exactly. This shows you the potential of quantum computer. And so that's what we are currently developing.
Yes, indeed. That's a very exciting prospect to see that there are problems out there that, you know, we think about computers and they can help for everything, but there are even problems that computers...
But they won't do they won't do Word or
No, that's for sure.
PowerPoint.
That's for sure. That's for sure.
Now, just to highlight also that quantum computing is not there to replace classical computing. But it's there for these very complex problems, which we as physicists and also in the science and in engineering and in optimization, etc., want to solve, which cannot be solved today because we don't have the compute power. And today we use approximations to get an idea of the solution, see some trends, and that's something. And the approximations, sometimes they work very well, but not always.
And let me give you a few more examples of things that are actually at the boundary, which is they're solvable by computers, but it takes forever to solve them. So in my field, actually, at CERN in Geneva, we collide particles. And when we collide the particles, we actually have big detectors, which are like big cameras, like on your phone, basically lots of those chips put together in very big cylindrical forms. And we look at the output of the collisions, and we need to understand what particles went in which direction and how they interacted with each other. And we basically come up with pictures which are like, equivalent to 500 or a gigapixel, 500 megapixel or a gigapixel images. And then we need to understand what happened there. And the problem is also one of combinatorics, maybe a bit less complicated than the ones that are intractable, but it takes for us a very long time to basically imagine where you have, like, in 3 dimensions, about 10 to 20,000 points that you have to map to trajectories of particles, but naively you would have to start trying, okay, are these two together working? With a third, does it work? No, it doesn't work, we try something else. And this, for a classical computer, takes a lot of time. We tried using GPUs, and we actually do that, so graphical processing units, which provide some level of parallelization, but the parallelization that we obtain there is not enough. So for us, what would be great is if we had a way to use a quantum computer that would actually give us the optimal solution to the problem of trying to identify the particles that are appearing in our detector much better. Of course, it's a challenge because we would need now big enough quantum computers that we really need to be able to operate on them. And then maybe on a more mundane level, maybe to bring this idea of, we humans have a lot to do with logistics, of course, right? We have a lot of shipping, a lot of things going around. And actually the logistics problem is very close to this 12 people in a party, that you really need to optimize a bigger network. And okay, you can try like play the bridges game of Heidelberg and see how you travel around, or you can rely on a quantum computer to do this. Now, I wanted to maybe go back to the topic of what a quantum computer looks like, not so much in the terms of, like what it does and this description of what it can do, but you mentioned that it would only be an assistant, let's say an accelerator, if we speak in those terms, to a classical computer. So why is that? I mean, what are the challenges of actually making a quantum computer and operating it, let's say?
Okay, so I mean, from the quantum computer, it's a universal computer which in principle can solve everything, right? If we have the ideal and error-corrected computer. Today, the quantum bits are not error-corrected. So, and typically we as consumers, we don't care about this, right? Because the computers you're using today, they're error-corrected. Which means in a classical world, it's very easy because let's say you have 3 bits or you have 1 bit, and but there may be a problem with your computer or some cosmic particle hits in and your bit gets lost, right? That happens. But today in computers, what you do is you use instead of 1 bit, and that's a simple version of it, you use instead of 1 bit, you use 3 bits. So if you do all your calculation, then you can check, do all 3 bits have the same number, or are 2 bits only have the same number and this other bit has an error, right? So if your bits have less enough errors, then this majority vote, which says, okay, if 2 bits still have the same number, then this is right and the other one is wrong, does the error correction. That's very simple for our, let's say we learned it over the many years we work on classical computer, how to do it well. And but the problem in quantum mechanics is that you have these probabilities. That's a strange phenomena. When you have a quantum bit, it's a certain probability of being in a certain state. And so, and if you measure it, what you measure is in principle the probability of being in 1 or in 0. So when you measure the state, you destroy the state, which is a problem because you can't copy it, right? And that's really the core of the problematic of quantum error correction. You cannot copy the information of a quantum state because when you measure, you destroy it. And so you have to figure out, so theorists have figured out that quantum error correction still works in many years back, theoretically. They have proved that you can do it, but experimentally it's pretty difficult because what you need is, besides of one qubit, you need other qubits around in order to detect without destroying the state of the qubit. And so you then measure the others, and then you know in which state your qubit is. So that's a trick, but it means you have a large overhead. And this means when I say these 200 qubits which you need error corrected for calculating the molecule, they need to be error corrected. So today you would need many, many more to do that error correction. And that's a lot. That's very, very active research. And there has been also a lot of progress to also reduce the number of qubits which you need. So that's one part. But I think I lost now the first question.
No.
So you see, it's very different, right? The type of computing is very different, and therefore it's also different how they look like. Today, also the quantum information is very, very sensitive. This means if you have a quantum information, then typically it decoheres with time. So this means it loses its quantum information because it's so sensitive. And then you cannot do a calculation which is quantum. So any light, temperature like we are in, quantum information doesn't exist. This is why we also not experience it in our daily life, right? This is why we are not seeing these strange phenomena of physics in our daily life, but only if we go to very cold temperatures in the physics lab, or if we go to very tiny structures or very different environments. But this is then only physicists because they look at it and then they measure it and then they try figure, they get used to it and understand it. So, but in our normal world, we only experience the classical physics. And so a quantum computer is therefore also physically very different because what we are using today in our machines, which we have as products, is a so-called superconducting quantum bit. And this lives at 10 millikelvin. So now you calculate, okay, what is Kelvin, right? 0 Kelvin is the absolute zero temperature which exists in the world, right? That's 0 Kelvin. And 10 millikelvin is just 0.001 degree above the zero temperature. So it's like minus 273.14. So it's really cold. It's like 100 times colder than in outer space, right? So it's really cold. But we learned over time to build those machines that today we can just plug and play, right? We can plug the button or push the button and then it gets cold and it's fine. But there has been a lot of engineering done over the last 100 years to come to that state. And you use liquid helium, you use a different state of superfluidative helium, helium-3, helium-4, so I don't want to spare you the details. But that's under control. But it needs a bigger machine, right? So the machine which we have today is about, with all the electronics and the vacuum equipment, because you need vacuum in order to cool down, because otherwise all the air, the humidity, the water in the air freezes, so you need to first have vacuum, then you need to cool it down, etc., etc. And you need to shield it, because every electron or every photon, every light which would come into will kill the quantum information. So that's why it looks very different, and the machine today is about like 2 meter times 2 meter times 2 meter. So I don't have it with me.
Of course. No, very exciting, very interesting. I mean, I can relate to this challenge of cold temperatures because at CERN, at the Large Hadron Collider, we're actually at 4 Kelvin. It's bigger. It's a 27-kilometer ring, so fine. Not the same scale, by no means. But 4 Kelvin is already a challenge for us to achieve, and we are still super high temperatures with respect to what you are talking about.
Yeah, but I think there's a big difference. There's a very big difference because you need the temperature in the whole ring.
Exactly.
Right? We need that temperature only in a very tiny volume. So how it works for our asset, we start at 300 Kelvin and then we go down in stages, and the volume where the processor sits, which is also small, right, like 2 times 2 centimeters or something like that, that is a very small volume. Only this chip has to be cold. Everything else can be at higher temperature, right? And the other thing is, what is also different in our technology is that we work in a superconducting state, which means you may have heard superconductivity is a state where the material has no resistance for current. And that's, our copper currents which we use, they are low resistance, but they have a resistance, right? But at superconductivity, you have no resistance, which means you don't generate heat during the calculation. So you don't need a vent, right? Our today's computers, they generate a lot of heat, and that's actually a big problem. That actually limits also the frequency at which we can run the processors because of the heat we can take away from before melting the transistors. And so at the superconducting state, the qubits work. We don't have resistance, therefore we don't need to counter or to take away that heat, and therefore it's possible. It's much easier possible than that we can go to that temperature.
Yes, very much, but very challenging still nonetheless. And thank you for explaining the fact that, okay, quantum computers will remain something of a more infrastructure-based thing that you can access maybe on the cloud, and we'll get to that in a moment. One thing that I would like to bring maybe to the audience before we move to quantum machine learning, and because this is really the crux of the item. So there are 2 points that I think are worth discussing, and one of them that I'll cover now is that quantum computing is a technology that allows these breakthroughs that we mentioned, but then there is the possibility of those breakthroughs to have an immediate impact. And for example, you all hear that cryptography will be dead and destroyed because of quantum computer, and that's true for certain early versions of what cryptography was done. And these technologies are coming very quickly because we have maybe access to some machines sooner than later. But the point that I wanted to come to is basically try to give the audience maybe an idea of the roadmap of where we stand in terms of computing, maybe making a parallel with the first invention of the transistor and how long it took us to get to our smartphones and everything like that. Where do we stand maybe on a very abstract level on that scale of development? So of course IBM got a very nice computer with about 1100 qubits out in December, but how does that correspond to the needs related also to this error correction that's systematically needed?
Okay, that's where do I start? I mean, if we look at the quantum computers today, just a brief history, right? In 1980, Feynman had this idea because he was frustrated by not being able to calculate this molecule. And then he said, if I would have a computer which uses the same physics like my molecule behaves, I could calculate it, right? Which is a very smart idea, but at that time it was not clear how to build it. So the theorists took quite some time to figure out how to build such a quantum computer, what is needed, how does the physical implementation look like, right? What are the properties a qubit has to have in order to do calculations with it? And all that took quite some while. My colleague, actually, David DiVincenzo, in 1994, published a paper where he showed 5 criteria for an experimental physicist to look for to build a qubit. So when these 5 criteria were published, then people, the experimental physicists went on and started to look at different physical systems where they could get these 5 criteria to build a qubit. And this was really a breakthrough, important paper that we as experimental physicists could look for the properties which are needed to build it, right? And so this happened in 1994, and then it took a while, until like 10 years, until the first qubit was demonstrated. There are different systems how you can build qubits. You could also use an atom. You can cool that atom also to very low temperature, and then use the energy levels in the atom to do a quantum computer. So there are many different ways. And the most advanced today are superconducting qubits, which we are using. And why we are using them? Because we think that these are scalable. We can build them on the typical silicon technology in our fabs. And they are also, let's say, easier to build than some other things. And we have learned over time how to build them. And in 2016, we have built the first 5-qubit processor. And at that time, I was actually on Yorktown also, where we built it, where we decided to make this already available to the world, to give access to researchers to start working with this 5-qubit processor. It's not many qubits, but the theorists who looked into error correction, who looked into algorithms, they were so happy to have something they can access to test now, because there was no experimental platform where they could test their theories, right? And so that was I think, a big moment also, and accelerated the research very much, that we opened that. And so we brought our systems into the cloud, and since then, also actually within IBM, we increased the teams a lot. We accelerated the progress because we saw also there is a need of the community, and there are also many applications, and we also internally accelerated the progress by having more people working on it. And so since 2019, where we demonstrated a 27-qubit processor called Eagle, each year we increase the number of qubits. So from 27 to 65 to 127. Actually, this is Eagle, 127. Then to Osprey, which is 433 qubits. And last December, we had the first time a quantum processor which reaches more than 1,000 qubits. And actually, there's no other which has more than 100 qubits in superconducting qubits. So they are not yet error corrected, but in parallel, we also increase and improve the quality of these qubits, that they have less error. So that's also important, that they have less error, that they're less disturbed, etc. And also the speed and how they are interacting with classical computer for certain algorithms. So we work on the hardware and also on the software, that people who are computer scientists and may not fully understand also how the quantum computing thing works at the bottom, that they can use and program. So if you know Python, you can in principle program a quantum computer. So of course the software stack is improving also, having access to more capabilities, which we still can tune in our electronics, but we make them available by writing the software also to everyone, and you can access it via the cloud. And so I think really it accelerated a lot. There are many people who have access already. There are many companies who started to work on use cases to identify what is the problem in my area, in my industry, where I could benefit of a quantum computer. And so there's really a lot of things happening. And we are moving on. We are also investigated a lot how we can further scale beyond 1,000 qubits. And our goal is actually to build in 2033 a machine with more than 100,000 qubits. And also implement error correction. We have right now implemented error mitigation. And that's also very important to understand the difference. Error correction is you really can correct the error. In error mitigation, you do not correct the error, but you understand the error and you can calculate back. So you can kind of go back to zero error, and thus you can also improve your result and get an error-free result. And that we have demonstrated last year.
That's great, and actually it's very exciting news because we managed to actually use these tools. I can talk from a user perspective, understand maybe the quantum physics or part of it, maybe not everything, but what I want to share is also the excitement of using these tools for the first time as a user, not having built them. So you imagine, I mean, when, especially going on to quantum machine learning as well, because that's the topic of today, but we wanted to set the basis. There was a question?
There was a question, yeah. Actually.
Oh, please, let's throw them a mic.
Need,
where's the box?
Here.
There, throw it. Just.
Thank you.
Thank you. This is so interesting. Just to give us a sense of the scale and what you can do, if you compare a computer with 16 qubits to what you have achieved now with 1,000 qubits, could you give us sort of a sense of the scale or speed that improves?
Yes. So actually, this is a very tricky question. It's very difficult to answer because in quantum computing you have different. Let's start in a classical computer. If you have more transistors, you can kind of scale your problem linearly, right? In a quantum computer, it depends also on the problem which you want to solve because there's different algorithms, and therefore and then it depends on how big is your error of the qubit. How many qubits do you need to solve the problem based on your algorithm, etc. So it's more complex. There's not a real number I can give you right now, but reducing the errors of the qubits is very important because then you need less error mitigation, you need less error correction. Then there are also different algorithms for error correction. So. With 1,000 qubits, we have also reduced let's put it different. So what is important actually is when you want to solve a problem, you need a certain number of qubits, and you need a certain number of operations to implement your algorithm to get your result. So therefore, we call this like the width, which is a number of qubits. It's the width, and then the length, which is the number of gate operations you need to do. And so this length and width actually is also called volume to some extent, but this is the important part, right? That you can keep those coherent. So if you have a higher width and length, then you can do many more complex problems. We have last year put out a challenge, which is we gave a promise and said, look, in 2024, we will provide you a compute capability of 100 times 100, which means we promise you have 100 qubits and you can do 100 gate operations in one day, because that's also important. How long does it take, right? In 8 hours, you will get the result of this compute back with no error. And so now the researchers have to think about what algorithm, what problem can I map to this compute capability and to provide value, right? So that's really the what many people are working on, also our researchers, to think about what is the problem, which is so complex that I cannot solve it in a classical computer, but may be able to solve it on this 100 times 100. That may be a better, shows a bit how we work in this space right now. But there's one other thing which I may want to mention. Last year in June, we published a paper where we went for the first time in competition with a high-performance computer. And so the high-performance computer in the Lawrence Livermore National Berkeley Laboratory, and we took one problem, which we said, okay, we solve it on our quantum computer, and you solve it on your HPC. And we used the calculation of the magnetization of a material. And we increased the number of qubits to use it, and we could do this with our 127 qubits. We could calculate an error-free result. The classical machine, the HPC, although very big, could not calculate this exactly. They could not exactly calculate the magnetization of this material. They used then approximations in order to get to the result, and also these approximations failed. 3 weeks later, after the publication, the classical approximation teams, felt kind of challenged, and they came up with better approximations for this specific problem, and could then come in this, achieve the same result. So you see, it's a very interesting phase because now we are really in competition already with quantum computers, with HPCs. And an HPC uses a lot of energy, right? There are megawatts of power which are going in this machine, whereas we need about 30 kilowatt. So it's really, it can make a big difference, and we are at the edge of providing a result that a classical computer cannot do, and will accelerate further.
That's very exciting prospects, and thanks for showing you what the capabilities are. Maybe we go for another question.
Yeah, hi, Gil Altrovitz, faculty at Harvard Medical School and Chief AI Officer at the Veterans Health Administration. So we have a lot, as you can tell, of medical kind of ones. And I did notice, I think there's at the Cleveland Clinic a new facility. And so I was wondering if you have kind of examples in medicine of where it's being used today in some way that, it's better perhaps than a traditional computer. And then two, what are ways that you're thinking about integrating, kind of the quantum computer and the regular computer? Because I think you were mentioning kind of competing against them, but if it could be cooperative, right, then you can maybe get advantages of both.
So yes, no, very good question. So actually, it's cooperative. Of course, we were competing with a conventional classical HPC. But what will happen and what we are working on is we call it actually quantum-centric supercomputing, because a quantum computer always also needs a classical computer for interaction, right? I mean, you need to control it, you need to program it. So you always have a classical computer. And it depends also you also need to optimize the architecture of the interaction between your classical computer and the quantum computer. There are certain algorithms also where you calculate a part of your problem on the quantum computer and another part on the classical computer. So you need to make them interacting in the most optimized way that you get your result also in the best way back, right? So that's what we are working on and what we also have demonstrated. We call this quantum-centric supercomputing. And Cleveland Clinic, as you mentioned, has partnered with us, and they have actually the first private company who bought a quantum computer from us, which is in Ohio. And they are very interested in looking and exploring and doing research in how to apply quantum computers for medical problems, right? And so, of course, I mean, they're the best team, as my understanding, in oncology. So these are problems they are looking in. And there is also their protein folding are examples which are very complex, cannot be calculated by classical machine. So these type of molecular predictions, right, predicting the properties of molecules, although the interactions between different molecules, these are research problems which are looked at. Examples. But you can also go into the healthcare organization, right? There are also optimization problems. There are also machine learning problems, which then are also looked at with a quantum computer.
Very exciting. So we started a bit late, as you probably all noticed, so we'll take a couple of more questions. So maybe from the back.
Hi. Thank you for the enlightening talk. And as you rightly mentioned that, not all problems can be put in the quantum computers, and there are certain problems only. So say, for example, if I get a bit more technical, of course, this is very simple for you, but in a sense that if we look at the Schwartz and the Grover structure, those are the problems which aligns to the quantum structure and where we can get the speed up benefit. But number one, is there any other such mathematical structure which is being investigated, which can give us also a quantum speed up beyond Schwartz and Grovers? That's number one question. And the second is quantum ML. Probably we didn't get a chance to come to that right now, but in case we don't, so I'll put this question, that there is this new development about quantum-inspired neural networks, which is around tensor networks, where we can use the quantum theory to get some advantage. So what do you think about that? Is that advantage really worthwhile, what the research is showing? And
So I mean, chemistry, people are using the variational quantum eigensolver, right, technique, which is where you use a certain the quantum computer for using the wave functions in order to get the interactions and use the interactions between the different electrons, etc., in order to solve the problem. So that's something where a clear advantage, because you cannot solve it, but your computer needs to be large enough and error mitigated. So that's the part we are on. And then what we also have investigated, some of it is like in quantum Monte Carlo, where there is not an exponential advantage, but a square advantage, which is proven and also shown on a small classical system. And there are also heuristics. And there's, of course, also a lot of development on looking into new algorithms. But the variational quantum eigensolver is someone which is very much investigated for molecular and materials part. And then in machine learning, one of the things is to use a quantum computer not for pushing through a lot of data, but for example, for support vector machines that you can use the higher dimensional information space in your quantum bit for then using, getting out better feature spaces, quantum feature spaces that you can get better machine learning models. These are examples.
And I can give maybe a little perspective because also we kind of left aside the quantum ML aspect because of practical situations, and everybody was excited also about the quantum end. But we in particle physics also tried to use, quantum machine learning in addition to machine learning to try to solve our problems. And from an experience of using them, what I can share is that first of all, we learn how to program those devices because we need to learn how to operate them, what was discussed previously. But then we are at this stage now where we have this tool, or we have quantum computers which have a roadmap of things that can be certainly solved with them. And then there is the area of quantum machine learning where we think we can combine the two. We see great opportunities if we manage, but we don't necessarily know the trajectory it will take and whether this tool is useful at all. So quantum advantage is something that there are different areas where we know or expect it to happen certainly, but quantum ML is one of them where in many cases we don't know if we can achieve that advantage even conceptually, and there are some cases where we know. And for example, in particle physics we use a lot of, at this stage, quantum inspired machine learning, or for example things like are completely classical but mimic a quantum world, for example a digital annealer, and we are trying to learn how to use this tool. And it's very exciting in this period because we have a tool, we hope it can do a lot, but we learn how to use it. And I find this extremely exciting because I don't think I've ever felt this excitement since a long while, because you really, okay, can we make something out of this? And it's back to the stage about, like, going back to what was said about AI and electricity, that, okay, is electricity of any use? So the question is quantum computing of any practical use, except maybe for, decrypting private communications? And we're learning this, and so that I find exciting. So unfortunately, we didn't talk much about more aspects of ML, but I want to give the feeling to the people that it's not something which is like just throw more compute at it and quantum computing will provide that compute. There are many, many things, like for example, quantum machine learning enables you to, okay, we have machine learning working on classical data, and we wish that quantum computers will help us harness that classical data and train our models better. That's sure an opportunity. But there is way more, because actually you can use quantum data from quantum sensors and actually do new things that are unforeseeable before. And this is an area that I'm not directly involved, but can provide further excitement because, quantum computers can operate on the quantum world, and that quantum world is either a classical representation of our classical problem that we transcode, or something completely new from quantum sensing. So I just wanted to give this perspective because we kind of moved past it, but I think we would go back maybe to questions that were in the room. So I think there was somebody in the back, and then here, and then here.
Hi, I was hoping you could speak on quantum encryption and how IBM or the sector overall is tackling this method of cryptography.
Yeah, so a short algorithm was mentioned. Sorry. So a quantum computer, because of this exponential power and an algorithm which has been invented in 1996 or something like that, or 94 also, is the so-called Shor algorithm, where you can then find the prime number in a very, very big number. And this is a big problem for a classical computer. This is why we use it for encryption. Because if you have a big number and you ask a classical computer to find the prime number, then he has to go sequentially through everything, right? Which takes a tremendous time. This is why we use it for encryption today. A quantum computer, however, could solve this problem in like 30 seconds. However, it needs to be a high number of qubits. It's not super clear how many, and it needs to be error corrected. And of course, there is a risk in the future that there is a computer which is large enough to do that problem. So any data which people may collect today can then be decrypted in the future. Therefore, we are working since many years actually on new encryption techniques, which are so-called quantum safe, which means even a quantum computer cannot decrypt that algorithm. And over the last 7-8 years, there has been also an international competition of the encryption researchers, Quantum Safe, where they have come up with, I think at the beginning, there were over 70 of those algorithms. They were tested many, many years. And 1.5 years back, the NIST selected 4 of them to make as a standard. And that is currently going on. And so if you use those encryption methods, which are based on a quantum safe algorithm, an algorithm which is cannot be broken by a quantum computer, then you're safe. And so you can, there's a lot of activity also. The US also has requested, the government has requested that the government facilities also start to have a strategy on how they implement this new encryption technologies in order to be ready and not have people right now collecting data and then decrypt later.
Yeah, would you just be able to follow up on how this would be able to be implemented, as a quantum computer could jeopardize, the majority of computers in the world?
No, but the data is the data is encrypted in a way that it can't be decrypted by a quantum computer. Right? So that's really when you generate the data, then you encrypt it already in the quantum safe way and cannot be decrypted by a quantum computer. That's the idea. And so these algorithms are already, you can use them already in storage, which we sell, for example.
All right, thank you.
Okay, unfortunately, we are a bit stretched by time. I have to ask if it's possible to stay a bit longer or not, and a message to no, okay. So we can take a few questions here among maybe the interested people when we go outside. But I'm sorry that we couldn't go through everything. It's been very exciting actually to see that, I was a bit worried when we started to say, okay, it's the last panel of the week. Who's going to show up? Everybody's already maybe preparing this ski weekend or whatever you're going to do after. So I'm very pleased that people came here. And of course, Heike provided great insights into the future of quantum computing. And so it was really exciting to be here with you guys. So thanks a lot. And I hope you enjoyed the session and in general the week. And thanks for being here.
Thank you. Thank you very much.